A common approach to figure out a reliable treatment method would be to analyze the days it takes the patients to be cured. We can use a statistical technique which can compare these three treatment samples and depict how different the samples are from one another. There is such a technique which compares the sample on the basis of their means. Hello everyone, good morning. Teacher Melanie M. Bacones reporting. Today I am going to discuss with you all about Anova. Anova stands for Analysis of Variance, is a statistical test used to analyze the difference between the means of more than two groups. It is also a statistical technique that is used to check if the means of two or more groups are significantly different from each other, or to split and observe aggregate variability found inside a data set into two parts: systematic factors and random factors. The systematic factors have a statistical influence on the given data set, while the random factors do not. So, based on analysts, they use ANOVA test to determine the influence that independent variables have on the dependent variables in a regression study. A two-way ANOVA is used to estimate how the mean of a quantitative variable changes according to the levels of two categorical variables. Today, I will try my best to impart with you my own understanding about these topics. The one-way versus two-way ANOVA. What is two-way ANOVA? When to use two-way ANOVA? What are the three main advantages of two-way ANOVA? And lastly, two-way ANOVA application in a sample. So what is two-way ANOVA? Two-way ANOVA is used for data analysis when you have two independent variables, or two-way and two or more levels of either or both independent variables. It has many of the same ideas as one-way ANOVA, with the main difference being the inclusion of another factor or explanatory variable. So when are we going to use two-way ANOVA? Okay. You can use a two-way ANOVA when you have collected data on a quantitative dependent variable at multiple levels of two categorical independent variables. We have a quantitative variable which represents amounts or counts of things, and a categorical variable which represents types or categories of things. Okay. In a quantitative variable, it can be divided to find a group mean, while a categorical variable level is an individual category within the categorical variable. So what are the three main advantages of two-way ANOVA? It is more efficient to study two factors simultaneously rather than separately. We can reduce the residual variation in a model by including a second factor thought to influence the response. We can investigate interactions between factors. The interaction between two variables is usually the most interesting features of a two-way analysis of variance. When two factors interact, the effect on the response variables of one explanatory variables depends on the specific value of levels of the other explanatory variable. Okay, for example, the statement being overweight caused greater increases in blood pressure for men than for women is a statement describing interaction. The effect of weight is the factor number one, categorical, overweight or not overweight, on blood pressure. The response depends on gender. Factor number two, categorical, male or female. The term main effect is used to describe the overall effect of a single explanatory variable. For our previous topic lesson, that there would be two main effects: the effects of weight on blood pressure and the effect of gender on blood pressure. The presence of a main effect might not necessarily be useful when an interaction effect exists. For example, it might be sensible to report the effect of being overweight on blood pressure without reporting that there is a difference in the effect of being overweight on blood pressure for men and women. There are many types of interaction which can often be seen from patterns in graphs. We will study some types of example in the following. Okay, example number one. A. The Bureau of Labor Statistics collects data on earnings of workers in the U.S. classified according to various characteristics. Here are the mean weekly earnings in dollars of men and women in two age groups who were working full-time in the first quarter of 1997. For this table, we can see the ages between 16 to 19, 20 to 24. For women, ages 16 to 19, the mean is and men 264, the mean is 251.5. While in the age of 20 to 24, the women and men mean is 317.5 with a total of 284.5. So in this side, the weekly earnings in dollars and the ages between 16 to 19 and 20 to 24 for women and men. So in our graph, the only two effects that are present are an effect due to age and an effect due to gender. We know that men make an average more than women, but there is no dependence on age to determine the amount that men make more than women. It clearly shows the existing of main effects. From the plot, we can see that on average, men earn more than women, indicating an effect of gender. We can also see an effect of age since the older group makes on average more than the younger age group. So question, what about the interaction between gender and age? Okay, an interaction is present when the main effects cannot provide a complete description of the data. Therefore, since there is no dependence between gender and age, there is no interaction effect. The parallel lines in our plot usually imply little or no interaction. Okay, example. The survey described in 1A also give weekly earnings for groups of older workers. Here is the complete table. It demonstrates both main effects and an interaction between gender and age. So as the age of the workers increases, the earnings increase except in the last age group. So this one, 55 to 64. We also see a main effect of gender on earnings. However, our interaction shows that the amount by which the men earn over the women depends on the age group. So in this case, The main effects do not provide a complete description of the data, since now the gender difference in earnings depends on which age group we examine. So therefore, there is a very strong interaction present, and our main effects don't provide us with enough information to get an accurate idea of the relationship between age and earnings as well as gender earnings. Example number 2. A study of the energy expenditure of farmers in Burkina Faso collected data during the wet and dry season. The farmers grow millet during the wet season. In the dry season, there is a very little activity because the ground is too hard to grow crops. The mean energy expended in calories by men and women in Burkina Faso during the wet and dry season is given in the following tables. So we have here two seasons, the dry and wet, men and women, and the mean. Okay. So during dry season, men and women had an mean of 2315, while in wet season, both men and women have mean of 31.75. So in overall, both dry and season, their mean is 2745. Okay, during the dry season, both men and women use about the same amount of energy. However, during the wet season, both genders burn more calories. So therefore, there is an effect of season on the number of calories burned. While during the wet season, since it is the custom for men to do most of the field work, they use more energy on average than women. So therefore, there is an effect of gender on the number of calories burned, but only in the wet season. So there is an interaction between gender and season, as well as main effects of both factors. The two-way ANOVA model. When discussing two-way ANOVA models, we will use the labels A and B to represent our two factors. We use I to represent the number of levels of factor A and J to represent the number of levels of factor B. Therefore, we call the general two-way problem an I-XJ ANOVA, since every level of A is combined with every level of B so that I-XJ groups are compared. In examples, we will use the factor names so that we can easily see the meaning of each variables. So the sample size for level I of factor A and level J of factor B is NIG. The total number of observation is N is equal to summation of NIG. J. Okay, example number 3. A company wants to compare 3 different training programs for its new employees. The training can be given for 8 hours on one day or 4 hours on 2 consecutive days. So each of these programs takes 8 hours to complete. The next 120 employees that the company hires will be the subject for this study. After the training is completed, the employees are asked to evaluate the effectiveness of the program on a 7-point scale. So they are going to identify the response and explanatory variables, state the number of levels for each factor, the quantity of I and J, and the total number of observation for the quantity of N. Solution. Explanatory variables. Number 1, the training program is the quantity of I is equal to 3 levels. The number 2, the manner in which the employees does the training is the quantity of J is equal to 2 levels. For 8 hours, for 1 day. Training must be 8 hours for 1 day or 4 hours on 2 consecutive days. What the response variable, the 7-point scaled effectiveness score total number of observations is n equal to 120. Okay, for our two-way ANOVA, we assume to have independent SRSS of size nij from each of I, X, J normal populations. So the population means mu Ig may differ, but all population must have the same standard deviation. So let Xijk be the kth each observation from the population having factor A at level I and factor B at level J. Since our observations differ from their mean by a value of summation of Igk to the quantity of Xijk minus mu Ig is equal to summation of Igk. So therefore, we can write our two-way ANOVA model in the form of Ixjk is equal to mu Ig plus the summation of Ijk. So in this case, I is equal to 1, 2, L and J is equal to 1 and 2, J and K is equal to 1 and 2, and Ij and the deviation summation of Ijk are normally distributed with mean 0 and standard deviation. So as in the previous discussion, we can describe our model by data is equal to a fit and residual. Fit plus residual. So in this case, the fit part of our model is the means mu Ig. For the quantity, since we use each mean to describe each population. So the residual part is a deviation summation of Igk of the individual observations from their group means. Our population means mu Ig and the population standard deviations are all unknown. So therefore, we pick simple random sample SRSS to learn about the relationship between our factors and the response in our samples, and then use that to estimate the relationships in our population. The parameter estimates the population mean for the group with level I of factor A and level J of factor B is represented by mu Ig, so it can be estimated by this formula. Since every population standard deviation is assumed to be the same in two-way ANOVA, we can pull all of our estimates, sample standard deviations, to give one estimate of the population standard deviation using this formula. Okay, SP2 is equal to MSE, and so the numerator of SP2 is equal to SSE, and the denominator is equal to DFE. Since we have summation of the quantity of 1 Nig negative is equal to N minus Ig o Lg, so we have N observations being compared to Ig sample means, just like in one-way ANOVA. Okay, for example, number 4, students in a statistic class gave information on their height and weight and reported their perception of their weight about right, underweight, overweight. So the body mass index or BMI was calculated for each combination of student gender and perception of weight category. BMI is equal to weight over height. So calculate each sample mean based on the data. Okay, so we have here perception of weight, the underweight, about right, and overweight. So for female, the ages between 18 to 21, underweight na siya kung ang iyang timbang, no, kung ang iyang timbang kibali, no. Then about right, kung mo gain siya og 20 to 23. Then overweight po siya if mo gain siya og 22 to 26. Well, the normal weight to the underweight of male is between 20 to 23.8. About right is 22, between 22 to 26.5. And overweight between 26.4 to 28.1. But remember that the weight of the both male or female will be based or depend on their age and height. Solution, so let factor A be the perception of weight and let factor B be gender. Within a factor A, let level 1 be underweight and level 2 be about right and level 3 be overweight. So within factor B, gender. Let level 1 be female and let level 2 be male. So U11 corresponds the population mean BMI of underweight females. So 12 corresponds to the population mean BMI of underweight males, and so on. So to estimate these population values, we use XIG bar to estimate mu IG for I is equal to 1, 2, 3 and J is equal to 1 and 2. So, mo ni siya ang data no gathered. So, dili na lang nako siya isa-isa kon. So, makita na siya dira. So, X is equal to 11 bar 20.2 plus 20.6. Kanini siya the ages no katong sa babae, and then mo ni siya no mga between ages sa ilahang timbang. Bar just means that X has a bar over it, indicating a mean. Okay, so two-way ANOVA table. In two-way ANOVA, there are 3F statistics that are calculated and used in significance test. 2 that test for the main effects and 1 that test for an interaction. So therefore, the sum of squares for our fit or SSM is made up of 3 parts. The SSA or the sum of squares for factors ASSB, sum of squares for factor B, and SSAB, sum of squares for the interaction between factor A and B. Our total sum of squares, and the total degree of freedom are still the sum of the sources of variation and degree of freedom in our model. SST is equal to SSA plus SSB plus SSAB plus SSE. DFT is equal to DFA plus DFB plus DFAB plus DFE. When our sample sizes are different, do not be alarmed if our sums of squares do not add up to our given SST. When our sample sizes are different, this can cause sums of squares which don't add. Since we have I levels of factors A, DFA is equal to 1 minus 1. Since we have J levels of factor B, DFB is equal to J minus 1. Since SSM is equal to SSA plus SSB plus SSAB, and DFM is equal to IJ minus 1. DFAB is equal to the quantity of IJ minus 1 minus to the quantity of I minus 1, the minus to the quantity of J minus 1 is equal to the quantity of I minus 1 and to the quantity of J minus 1. So DFE is equal to N minus IG. So we have N observation and IG sample mean. So DFT is equal to N minus 1. Sa two-way ANOVA table, so we have here the sources, yung A, B, degrees of freedom, I minus 1, J minus 1, quantity of I minus 1, J minus 1, so NIG, NI, so sums of squares, and the mean squares, and the F. Hypothesis for two-way ANOVA to test the main effect of A. No main effect of A. There exists a main effect of factor A. F is equal to MSE over MSE compared to F to the quantity of I minus 1 and minus IJ. So remember that when we do a two-way ANOVA, we need to assume that our data is normally distributed and that the population standard deviations are equal. Therefore, we must make sure that twice our smallest sample standard deviation is larger than our largest standard deviation. To test the main effect of B, no main effect of B, there exists a main effect of factor B. So F is equal to MSB over MSE compared to F to the quantity of G minus 1 and minus IJ. To test the interaction of A and B, no interaction. There exists an interaction between factor A and B. Factor B. F is equal to MSAB over MSE compared to F to the quantity of I minus 1, quantity of J minus 1, and minus ING. Example number 5, when a restaurant server writes a friendly note or draws a happy face on your restaurant check, is this just a friendly act or is there a financial incentive? Okay, so psychologists conducted a randomized experiment to investigate whether a drawing of a happy face on the back of a restaurant bill increased the average tip given to the server. So one female server and one male server in a Philadelphia restaurant either did or did not draw a happy face on checks during experiment. So in all they drew happy faces on 45 checks and did not draw happy faces on 44 checks. The sequence of drawing the happy faces or not was random. So, identify the response and explanatory variables. State the number of levels for each factor to the quantity of I and J and the total number of observations for the quantity of N. Solution. Response variable. Tip. Explanatory variables is the gender of server for 2 levels and the message 2 levels, yes or no. The total number of observation is N is equal to 89. To complete the following two-way ANOVA table and then perform the appropriate F test for main effects and interaction and state your conclusions. Try to fill the table on your own. So you are going to answer this later. If we have still time. Okay, so this would be the solution. Okay. So no main effect of message. Null hypothesis, a main effect of message exists. So test statistics. So this will be 14.7 over 100.9. 109.8 is equal to 0.134 with numerator degrees of freedom 1 and denominator degrees of freedom 85. So the decision rule, this test statistic corresponds to a p-value of 0.7152. So we do not have any evidence to reject the null hypothesis that there is main effect of message on the average amount of server gets tip. Okay, so that is the null hypothesis is the no main effects of gender. Test statistic test statistics is equal, F is equal to 2602 over 109.8 is equal to 23.7 with numerator of df is equal to 1 and denominator df is equal to 85. So decision rule, this test statistic corresponds to a p-value of less than 0.0001. So we have very strong evidence that a main effect of gender does exist. Okay, for the null hypothesis, so no interaction effect between gender and message, and interaction effect between gender and message exists. So test statistic is F is equal to 438.7 over 109.8 is equal to 4.0. So with numerator df is equal to 1 and the denominator df is equal to 85. So the decision rule, this test statistic corresponds to a p-value of 0.0487. We have evidence to reject the null hypothesis of no interaction at the 0.05 level. So we have reasons to believe that there is an interaction effect. Okay, for the assumption for two-way ANOVA, so the population from which the samples were obtained must be normally or approximately normally distributed. And number 2, the samples must be independent. And number 3, the variances of the populations from which the samples were selected must be equal. And lastly, the groups must be equal in sample size. So this is the formulas for two-way ANOVA for an equal frequency. No? Okay, so that ends my my little interpretation about the topic, and I am not sure if I was able to impart with you the exact knowledge that you wish to have. But to further or to give you more example or to explain more about the topic, let me show you this video clips. No, I search from the internet. No, and if you do have additional information or additional ideas about the topic, I am very much willing to have it and to learn also some ideas from you. So, and for more clarifications, ayaw lang ng questions, no? Joke. Bitaw, we can, maybe we can have that after this presentation.
Let's say you want to find out if the beverage that people drink affects their reaction time. So you set up an experiment with 3 groups of people. The first group gets water to drink. The second group gets some sugary fruit juice. And the third group gets coffee. Now you test everyone's reaction time. And you want to know if there's any difference in reaction time between the groups. The null hypothesis says that the mean reaction time for all 3 groups is the same. If there were only 2 groups, you could use a t-test to find out if there's a difference between them. But when you have 3 groups or more, you need to use a different approach, the analysis of variance. When you do the experiment, the scores won't all be the same. The total variation of all the scores is made up of 2 parts. The variation within each group, because the people in each group have different reaction times, and the variation between the groups, because the drinks you gave each group are different. Here's an example. Look at this set of scores. They've been sorted into order to make it easier to see the patterns. You can see that there's a lot of variation within each group. Some people are faster and some are much slower. But all the groups look pretty much alike. There's not much variation between the groups. In this case, you'd say that most of the difference is due to the people, and the drink didn't make much of a difference. You would accept the null hypothesis, that the type of drink doesn't have any effect on reaction time. Now let's look at a different set of numbers. In this case, all the scores within each group are very close to one another. There's not a lot of variance within each group. But the groups are very different from one another. There's a lot of difference between the groups. In this case, you would reject the null hypothesis. In this case, the type of drink makes a big difference. So here's the idea behind analysis of variance. Figure out how much of the total variance comes from the between groups variance and the within groups variance. Take the ratio of between groups to within groups variance, and the larger this number is, the more likely it is that the means of the groups really are different and that you should reject the null hypothesis. In the examples, it was obvious where the variance was. Now look at these numbers. You probably can't tell if there's a significant effect because it's not clear whether there's more variance within groups or between groups, or how much. The calculations show that the ratio is 4.27, which has a probability of 0.04. So in this case, you can reject the null hypothesis. With these numbers, the drink you give the people does have an effect on their reaction time. What's that 2, 12 doing there? Those are the degrees of freedom for variance between groups and variance within groups. And here's how you calculate the degrees of freedom when you report results for analysis of variance. This trick of separating the variance not only works when you have 3 or more groups, it also works when you have multiple variables. For example, if you test 3 groups for reaction time in the morning, and you test another 3 groups in the evening, an analysis of variance can tell you if there's a significant effect for the type of drink, or if the time of day makes a difference, or if there's some interaction. For example, coffee might be more effective in the morning than in the evening. So to recap, here's the main idea of analysis of variance. You figure how much of the total variance comes from between the groups and how much comes from within the groups. If most of the variation is between groups, there's probably a significant effect. If most of the variation is within groups, there's probably not a significant effect.
Okay, so that ends my report, and I hope that I was able to give justice on the topic. Thank you so much for watching the video and for listening my report. Once again, good morning and God bless everyone.